All right, coming at you by popular demand. Let's just do a little audio rendition of the Unit 3A review. So I already have the solutions laid out, so I'll just talk our way through it. And I know that's pretty efficient, so hopefully it'll help you guys out. So let's go do this thing. All right, so here we go. So when we started this whole shindig, we started off with talking about the derivative of a simple power function. So the first thing that I chose to do is I said, well, I see that 4 over x. I don't really want to do low d high and all that stuff, so I made it a 4x to the minus 1. That allowed me to come up with a straight power rule problem. This is actually a completely valid final answer, but usually people would choose to write it as 4 over x squared because cognitively that's just easier for people to understand than having that negative exponent. So for part B over here, we changed it up a little bit, but that problem is a little bit harder because as you can see, we do have a little bit of a product going on. I have 5x plus 7, which I kind of referred to in my head as f, and the tangent of x I refer to as g. So if I did a little f prime g, f prime being 5, g being the tangent, plus g prime f, I just got to there, and I know that a lot of you probably want to do something to simplify that because we've worked a lot about simplifying, but it turns out that's about as good as we can do. All right, let's move on. Now, I got no choice. I'm going to have to do a low D high. So we're going to do a little bit of a low D high minus a high D low. We're going to square the bottom, and away we go. So I went through that process. Here comes my low. My D high is 3. High is right here. D low is there. And then I squared the bottom. Now, in this particular case, we could leave it there, but that's really kind of frowned upon. We really should simplify. So I did a little bit of distribution. I saw 3x cubes here. I saw negative 3x cubed there, or negative 9x cubed there. I kind of simplified that down a little bit and came up with that answer, which isn't exactly a simple answer, but about as good as I can do. And then last on that top section, again, another version of a product rule. And a lot of people do see this x minus 1 and they're wondering if the 1 is inside that sign, yes or no. And the answer is no, because there would have to be a parentheses right inside here if it were. So I just called 15 sine x minus 1 f, and that's g. So I did a little f prime g plus g prime f. And if you look at that, f prime, the derivative of 15 sine is 15 cosine, and the derivative of the 1 part is 0. Now, the one thing about this particular story that is nice is as we went through both halves, we got an e to the x in the front side of the equation, and we got an e to the x in the back side of the equation. So I wasn't able to do anything really helpful in this problem, but in here I was able to factor an e to the x out of both, which did make the problem maybe a little bit nicer to look at. That doesn't always work, but in this particular case, it did. All right, so let's move down a little bit. So in this next question, I'm being asked to find the second derivative of 1 over x plus 1. So just like the question number 1a, I chose to think of it more as a power rule, as x plus 1 to the minus 1. So of course, to take that derivative, I would just get negative x plus 1 to the minus 2. So that's just d dx, which unfortunately is not what we wanted. That's just the first phase. So I needed to take the derivative now of that final answer. And so since this was the derivative, if I took the derivative of it, the power rule says drop that negative 2 in front, and we have x plus 1 to the minus 3 since I brought the exponent down by 1 more. Hey, what do you know? That exponent of a minus 3 means we could write it more simply as 2 over x plus 1 cubed. All right, almost done with the first page. Boy, I don't know about this one. Okay. Formal definition, that's a rough one. So what we notice in this front half, this is f of x plus h minus f of x all over h Little fraction buster. Oh, terrible long distributive property. But all sorts of good things happen in that problem. Everything cancels except for those two pieces. And I got a pretty nice little value. Now, to continue on with that, really, that was just part of the question because I wanted to know a little information about it. Like, what is the derivative at 6? So if this is k prime, then k prime of 6 would just say to plug in that number 6. And if I did, I just plugged it in. I got -7, so the slope was 7. So if we're looking for the tangent to that curve at 6, well, the first thing I needed to know was what was the y value. So I did have to go back to the original function k, and I had to plug 6 in right here, and I get 6 plus 2, which is 8, 6 minus 5, which is 1. So keep in mind that if you have the tangent or the normal to the curve, you must not only have the slope, but you need a point on the curve. So from the original equation, I found out that 6 gave me 8. And now that I have the 6 and the 8 and I have my original slope, point slope formula, I've got what I need, and that's going to be an amazing answer. All right, so that was page number 1. Let's go into page number 2. Now, page number 2 starts in a bad place, doesn't it? That is the formal definition of a derivative of an irrational function. So I did f of x plus h minus f of x over h. I did the big old fat conjugate right here. And so I had h times ugly. And on the bottom, I also have ugly. But the cool thing is when you distribute, these two pieces create that piece. These two create that, and the outer and inner portions of our full distribution just cancel out, which is why we did it. So in one step, it looked really bad, and it started getting better. Of course, a little distribution, you can see it even getting better as the 2x's and the 1's go away. So the entire numerator just was 2, which is hardly anything. But in the denominator, I've got this root and this root are basically the same thing. If h goes to 0, I've got 2x minus 1 and another 2x minus 1, so I have 2 of them. And that's why I saw those two 2's and I went ahead and canceled them. Now, of course, if we wanted to know, hey, what's g prime of 5? I just want to plug the number 5 into this thing. And of course, 2 times 5 is 10, minus 1 is 9, so 1 over root 9 is a third. So I had a nice little slope of a third. Just like the previous question, to find the normal to the curve, I had to go back and plug 5 into the original equation to find out where the point was. There's my 5, 3. And then instead of using a slope of 1/3 like I would have for a tangent line, a normal is an opposite and a reciprocal. All right, moving down a little bit. Oh, these are kind of fun. We got some of these problems with tables. Now, when the table hits, I've got, suppose that h is this function 5 times f over g. So I wanted to take the derivative right away. So I did a little low d high minus a high d low over the square of what's below. And then I was able to cherry pick the g of x, keeping in mind that I wanted to find out what happens at 3. I could say that g of 3, that would be right there, that's -1. I could sign f prime of 3, that was right here, -4. And I keep picking these values off as they go in. I plug them all in. Nice, easy set of data values. Just plug right in off of this top line right here. And just so happens, I got a nice, easy number of 115 over 4. Interestingly enough, the denominator became quite simple and pleasant. The only thing that was bad about that problem is that pesky 1/4 right there sort of messed up the whole works. Now, we know what this one is. This is the one place where I allowed chain rule to leak back into our story. If you take f of g of x and you try to take the derivative of f of g of x, then what you would have is f prime of g of x. So keep in mind, peeling the onion, we took the derivative of the outside portion times the derivative of the inside portion. So that's what I did down here. So I just wrote this out. And then, of course, if we wanted to plug in the number 3 in both places, again, g of 3 was sitting up here, and g of 3 was -1. G prime of 3 is -1/4. But unfortunately, this is f prime of g of 3. So if g of 3 is -1, I really need f prime of -1. And I got a fairly simple little number. And then, of course, the equation of that tangent line, I need to find out what the original point was. So I did find h of 3. And when I plugged in 3 and I went and got it, I got -35. And of course, I'm borrowing the tangent from this portion right here because it was the tangent to h. And remember, h was originally defined as the function with the 5 f of x's over g of x. So that was page number 2. All right, going on to page number 3. All right. Now, this is a cool little problem because we are going to prove something, which is nice because if you ever want to prove something, it means you already know what it is that you're trying to prove. So I started with the derivative of the cosecant, which is negative cosecant cotangent. And then I needed to take the derivative of that, because if I took the derivative of the derivative, that would be the second derivative. Derivative of f is right here times g, and notice there's a double negative, plus the derivative of the cotangent times the first. So you want to remember the derivative of cosecant is negative cosecant cotangent, and the derivative of cotangent is negative cosecant squared. Try to say that 2 times fast. Now, number 5, one of my favorite kind of questions is the definition of differentiable implies something else. So you want to keep in mind that if you are talking about differentiability, you must first be continuous. So the first thing I did is I looked at the function and made sure that it was in fact continuous. So I looked at what happens as I approach the function from the left. I also looked at what happened from the right, and if it's continuous, those two values, in fact, have to be the same. So if I plugged in -1 here, I'd get -a plus b, and if I plugged in -1 in the bottom function, I got that. And just really lucky, this does not always happen, but in this particular story, the b's totally went away, and I found out what a was. And then I took the derivative of both, top and bottom. And not only did their limits of the function have to be the same, the limits of their derivative had to be the same. So I took the derivative of each and set them equal. And since I know what a was, it works. However, you do have to be aware that sometimes you won't know that information quite that quickly. Sometimes you're going to get 2 totally separate sets of equations that both have a couple of unknowns that you can set up and solve. In fact, I think the one on the test, nothing goes away and you end up with 2 equations with 2 unknowns, and then you have to kind of stack them. All right, almost done with that. I saw some places where this thing was not differentiable. To be differentiable, as I said in number 5 right here, is it has to be continuous. So clearly f is not continuous at a because it is not continuous. I also noticed that at b and c there are cusps. So if you take a look at the limit as you approach either b or c, you don't get the same value approaching that point from the left or the right on that derivative. So that makes it non-differentiable. And of course, d, we talked about this in class, that's a bad guy because it's vertical. And if it's vertical, even for a moment, it's not differentiable at that place. Okay. We're almost done with the first couple of pages, and then I'm going to kind of reset this video. So number 7 is very much like one of the previous problems where I did a little low d high minus high d low, and I cherry picked these data values up here. Same thing on b. Low d high minus high d low. The answers look a little bit ugly, but it's not too bad. For G, this is an actual chain rule problem, very much like I believe it was number 4. But G prime of f of x times f prime, if we plugged in 4, the tricky part here is this is G prime of f of 4. And so f of 4 being, hey, I'll be with you guys in just a minute, you're fine. F of 4 is in fact negative 6. So even though I'm talking about what happens at 4, this part has to actually ask about negative 6 because of chain rule. And although now we're going to do something a little bit different in implicit derivatives, this time I didn't choose to cube both sides like we did today in class. I just went for it and I did a little product rule. That's 1/3 of x plus 2 to the minus 2/3. And then I decided to take the derivative again. So if I took the derivative again, I'd multiply and extend this down by 1. Extending this to find the equation of the tangent means not only do I need the coordinate at 6, which I found right here, 6, 2, but I also need to know the slope at 6, which I plugged in right here, and that was kind of ugly because 6 plus 2 is 8, and 8 to the minus 5/3, and then of course times negative 2/9 is 1/12. So again, I found the point right here. You can see the remnants right here. I also had to find the slope. This was a little bit of a chain of events to get down to this 1/12, but keep in mind our calculator does a pretty good job on that. Gets me to here. And last, if I wanted to find G double prime, I wanted to review this guy right here, because this was F prime, this was F double prime, and this is a measurement of something that we haven't talked much about yet called the concavity. All right, let's try to finish this thing down. Okay. Number 9. I wanted to know where the slope of this thing is in fact negative 11. So I just took the derivative and I set it equal to negative 11. And I'll be honest, I cheated and I used my quadratic formula solver and I found out what happened. But keep in mind, I knew what x and x was, but I needed to go back to the original function to find the 40 and the 2/3, because you don't stop there. You have to go back to the original to say where it happened, but also what happened. All right, considering the quadratic, finding the tangent, I don't think is too bad. I went ahead and I took the derivative right there. I plugged in 2, so I found out a point and a slope. That was no big. That was a nice, easy one. But finding the equation of the tangent to the curve that passes through 2, negative 2, this is where the problems get a little bit tough, because 2, negative 2 is not on the curve. So one of our stipulations for finding the equation of the tangent to a line when the point is not on the curve is we had to have them have the same slope, and we also had to have them intersecting, or in other words, sharing a point. So I first went in and I took the derivative of this, and I got y prime is x minus 4. But I also know that I wanted it to go through the coordinate 2, negative 2. So I took the y plus 2 and the x minus 2, but this slope that is sitting right here, I chose to replace that slope with x minus 4, which created this kind of quasi-quadratic. It really shouldn't be a quadratic, but it kind of looks like one because I haven't yet figured out what that m is. So phase 1 down, I made sure that they had the same slope. This one has a slope x minus 4, so does this one. So last part, I needed to make them intersect. So I did set them equal to each other. This time I didn't cheat. I went ahead and I did it all the way through, and I found out the places where they did in fact intersect. But if I know what x is, then I know what the slope is right there. So if x is 1, then the slope is in fact negative 3. And if x is 3, then the slope is in fact negative 1. So you'll notice I came to this equation right here, and I've used the values of x that I indicated to find those pieces of slope. Okay, number 11. Maximum height reached by the ball would be the moment when it stopped. So I took the derivative and I set it equal to 0. Now that's the time when it happened, but that's not going to tell you what happened. So I took the 12.2 and I plugged it into the original function to find out what that position or that height was of that. I personally got that value and I did a y1 of 12.245 to get that number. I didn't literally plug it into the original equation. I allowed my calculator to do some of that handiwork. Okay, and part B. What's the velocity of the ball when it's 400? Well, when it is 400 meters, that's a position. So I took the equation of its position and I set it equal to 400 and I used my quadratic formula and I found these. And one thing to note is part of the design of that program is E and F are the two answers to the quadratic. So what I know is where those things happen. So I came into my velocity equation and I plugged in the velocity at 3.906 and 20.58. And what's really cool about this, at least to me, is it kind of confirms when I did it, the velocity should be the same going up, but in reverse of what it is going down. In other words, they have the same speed, which is why it's not a good idea to shoot a bullet up into the air, because whatever speed it goes up with, it's going to be coming right down on your head or somebody else's head if you shoot it up in the air when you're all excited. And here is the pain problem, and this is the last one, and then I got some people I think want some help, and then I'm going to help them. So here we go, last little piece. Instantaneous velocity, how fantastic. That's just the derivative of our position, so Mamo did that. Acceleration, of course, is the derivative of our velocity, so I've got that laid out. So if I wanted my instantaneous velocity, I just need to take this velocity equation right here and plug in 10, which I did. Acceleration at 10, I got my acceleration and I plugged that one in too. But of course, now we got to actually do something with this problem, not just have the big pieces. So a particle will be at rest when its velocity right here is equal to 0. So of course I was super lazy and I used my quadratic formula program on my calculator and I made a little map right here. My velocity was positive until 1.212, negative for a period until 7.6, and then positive again. Now of course the acceleration switched up at 4.444 because I just took this acceleration and set it equal to 0. And I noticed that since this is a positive sloping line, it would be negative to the left and positive to the right, which tells me in this chunk right here, it would be slowing down because the signs are opposite, speeding up in here, slowing down in here, speeding up out here. So we've got this little chunk, and that's why this is written in the way that it is, in these open intervals where it's speeding up and slowing down. Total displacement is a joke. It's literally like, where are you at the end minus where you were at the beginning. A lot of people forget this 36 piece, but this problem didn't start out at the origin. It actually already started out 36 units to the right of the origin. So if it landed at 144, it was already 36 units over. So S of 12 minus S of 0. Again, I just use Y1 of 12 and Y1 of 0. And everybody's least favorite question in the whole thing is we need to take a look at its velocity and find out what happened while it was going forward. That is this piece of the story right here. What is happening when it is going backwards. That's this piece of the story going right there. And then what is happening for the moments from 12 to 7.6 as it's again going forward. And again, distance is an absolute value, so I took each one of these. These again, I didn't go do them. I did Y1 of this minus Y1 of that. And I just picked each one of those out. I got 309.808, and that's how much wear and tear we had on our shoes or on the equipment, and that kind of finishes up our review. And that took a little longer than I thought it would to talk through that, but that's what I did. So hopefully that was helpful to you. Send me an email, shoot me a question if you got any. All right, see you guys. Have a good one. Bye.